Welcome back, and I hope that you got some time to spend on the last class, which is Mayer's theory, which is a formidable class. This is the second time we are doing it. First time we did a little bit more detail, but it's a very difficult thing, and I decided to review it once more, along with the revision of diatomic, monatomic, and diatomic and polyatomic gases, because these are fairly new things to students of chemistry for whom this course is designed. And so in chemistry, we do a large amount of body of work on phase transition. From the beginning of chemistry, from Van der Waals theory of gases, from phase transition, gas to liquid transition. See, in our even undergraduate chemistry, there is a big chapters and on phase equilibrium, phase transition, and precipitation. In chemistry, physical chemistry, organic chemistry laboratory, we are all the time doing melting as a test of a purity and identification. So phase transition very dear to a physical chemist, and physical chemist is mandated to explain these things. Now, there is always this curiosity, so why, how the raindrops form, how gas goes to liquid, then of course how ice melts and water goes into ice. What are the molecular processes? These are omnipresent, they are all around us, but it turned out explanation of them, understanding of them challenged the intellectual ability of man to a very high degree. And the people and the scientists who are involved in doing this are some of the best minds that we have produced in entire civilization. So I already described, and I hope you spend some time, and I encourage you to spend more time in understanding Mayer's theory, how intermolecular interactions entered the picture to Mayer a function, which gives us virial series and also tells us how one can envisage or picture gas to liquid transition as small clusters in a room, like for instance in this room, small clusters coagulate together to form a gigantic big cluster, almost the size of the total number of particles of the system, which is the liquid phase, which is the correct picture. Is that exactly what happens, that when a gas goes into liquid, then many clusters of smaller size, quite small size actually, can be clusters of the size of only maybe 20-30 molecules, not more than that. But many of those clusters, most of them still monomer and dimer, they coalesce together in a very short temperature span to form a gigantic cluster of Avogadro number of molecules. This happened in so sharply and was such a short temperature range that we call it a singularity. We call it that the properties, thermodynamic properties diverge. For example, you calculate specific heat, it diverges. So phase transition has then characteristics of this divergence, that things just fantastic things happen. But then how do I explain these fantastic things? Mayer's told us, okay, think in terms of small clusters, and they suddenly come together to become big clusters. But I told you that Mayer's theory, however beautiful it is, it breaks down because we don't get the cluster integrals, reliable cluster integrals. He told us how to do these things, but those things are very difficult. We cannot do, even now today we cannot calculate irreducible cluster integrals for linear-Jones systems of something more than the size of the, say for example, 10 particles together. There is a huge number of graphs that come in which cannot be evaluated, and 10 particles doubly connected will be 30-dimensional integral, which just is not possible. Actually, people in linear-Jones have done only up to 6. That by Lee and Hoover, who did this beautiful work, landmark work in about 30 years ago, but nothing more has been done after that. However, at the 1937-38, around the same time, when Mayer was developing his game-changing theory of in terms of graph theory, in terms of clusters, in terms of cluster integrals, one brilliant physicist called Landau. Landau was developing a simple phenomenological theory to describe the phase transition, and this is called order parameter theory, that went on to become the mainstream of phase transition study, that went on to develop many languages and went on to giving probably 10 or 15 Nobel Prizes in this area of phase transition. So, we will briefly describe Landau theory. We did it once before, but I am going to do it again, probably somewhat from different perspective. And as I go on this way, I will repeat things. So we will go a little at once, then go back, and then again go forward. So in that way, as I said, painting is a way to learn things. So this is a our picture of Landau, the great Landau, and did many things. And this is kind of a free energy diagram, which was inspired by Landau, that if gas to liquid, high temperature, in the temperature large, it is gas where molecules are far from each other, but in a liquid the molecules are together. So this is the kind of droplet, the small clusters of Mayer's theory, this one gigantic cluster that forms and the phase transition. But look at that, there is a barrier, it has to go over the barrier, and this free energy, by going around the free energy barrier, is also a very difficult process. But the appearance of this double minimum is the essence of the Landau theory, and this, when plotting free energy against the appropriate quantity on the x-axis with free energy y-axis is called Landau's energy landscape. So we will now do. So this is kind of thing from the book, that phase transition ubiquitous. It manifested large and very important thing of phase transition, large experimentally detectable change, large change, macroscopic change. So macroscopic change, but the macroscopic change takes place in infinitesimal change. That means I change something very small, but something very big happens. That means this is a small change in a control parameter leads to huge change, like the temperature at 100 degrees centigrade. I just make it, I reach 99.9 and make 100, that 0.1 degree centigrade leads to huge change. Similarly, ice, 0 degree centigrade, I make it 0.1 degree centigrade, ice melts. So the real thing to emphasize and note that infinitesimal change leads to a macroscopic change in specific heat, enthalpy, entropy of parts of the system. This is the subject of phase transition. This is great importance in most branches of natural and biological science, like helix coil transition in DNA and protein folding. These are kind of a cooperative phenomena. So what is the language here? The classification, that many molecules kind of acting together collectively to give rise to this act of macroscopic change. So this is one of the most fascinating field of condensed matter science or natural science, that how molecules talk with each other, the molecules collectively change over from one phase like gas phase to another phase like liquid phase. So how do I understand that? May I try to understand from intermolecular potential. That's detail, that gives us some picture how things are happening, but that fails to give us, fails to describe the generality of the phenomena. So we need a description which is simpler but which is general, which captures the essence of this macroscopic change in a thermodynamic property due to microscopic change, in infinitesimal change in a control parameter like temperature or density. So that's what Landau did. So I described it before, but I'll describe it a little bit more physically this time. So phase transition are very common, liquid, solid, magnetic transition, ferromagnetic, paramagnetic transition, ferroelectric, and all these things. Well known examples are ordered. These are many phase transitions here. So then we study, then we ask with three questions: what is what, why, and how? What are the characteristics of the phenomena? What is a phase transition? Why does it happen? That is the why. How does it happen? So how essentially brings dynamics, which we will do later, not today, and that we will describe why it happens. How do I describe in terms of phase transition? like I go back to Meyer's theory, Meyer says clusters come together. But how does it happen manifested in, how do I describe in free energy? This is what Landau did. And so Landau said, so there is again, this will be given to you, there is a large number of examples, paramagnetic ferromagnetic phase transition, liquid solid, gas liquid, order disorder in very common in solid phase, like alloys, binary mixtures, again they phase separate, in polymers, in superconductivity, in superfluidity, solvent, helix coil, there is just phase transition is all around us, and you have to give proper importance to phase transition, not just because it is all around us, but phase transition brings in, introduces some of the most common and most useful language to physical science. This is something we learn from, like the concept of order parameter, the concept of singularity, and these languages, free energy expansion, free energy landscape, all the language we routinely use, they started in this field of phase transition. So, I am talking a very elementary language, but those were the newcomers. This is a, I must emphasize, this is a very, very important thing. So, these are the examples of phase transition. Let me go through. So, all these examples, this is my favorite, is huge, is characterized by discontinuous, change of macroscopic variables, that is finite change of a macroscopic variable due to infinitesimal change. So, the thing to know, finite large scale change due to infinitesimal change, small change in some variable, and this is the hallmark of phase transition. So, if you say what is a phase transition, then this is the phase transition. What? This is the definition of a phase transition. What? So, I explained why. Now, these are the examples. We already did pressure against density in Meyer's theory. You know this. Then we always ask this in our interview of undergraduate students, and then we ask pressure versus plot pressure versus temperature plane. And this is solid, liquid, and gas here. And in our classroom, we find really very interesting things. Where students put gas here, solid here, and liquid here, and all kinds of things they do. But this is the phase diagram. So, this pressure, temperature, this is the triple point, and this is the critical point. You know all these things. Then the another representation. So, there are three representations. This temperature against density. Then this another temperature. So, this is the gas liquid coexistence. Then this beautiful way goes. So, this is the solid. So, I can describe the same phenomena in three ways. Each says something very interesting and new. Like here it says when this kind of van der Waals loop or the kind of spinodal or instability. Here these are the coexistence line. These are the lines along which gas and liquid coexist, liquid and solid coexist, solid and gas sublimation across that coexist. And here it says how gas liquid crystals are showing together in a beautiful way, including this in parabolic shape, inverse parabolic shape, which is showing you the bell shape, which showing you the critical point and all these things. So, these are the three representations. So, phase transition deals with this kind of graph. This is for gas liquid, this is a simple thing. I can draw identical thing for almost magnetic systems. Now, as I said, one of the very important contribution of the phase transition that goes on to many different fields of condensed matter science or even protein folding or any other things is the order parameter. What is an order parameter? An order parameter is chosen as a quantity which is 0 before the transition, but becomes non-zero afterwards. A clear example is provided by liquid solid transition. Where is the order? Also magnetic transition, that is the magnetization, is an order parameter. So, a system is 0 magnetization, non-magnetic before the transition. After the magnetic, when it becomes ferromagnetic, its magnetization goes up large. So, now gas liquid or liquid solid, the entropy is, so this is solid, this is liquid, entropy diverging. Then you look at specific heat, that is diverging. So, order parameter is a quantity that is 0 before the transition becomes non-zero. In solids, we will have some more examples there. For example, if I show liquid solid, so there is a random system, then that becomes periodic. And periodic I can expand it and reciprocal, that is vectors, you know this is expansion. and this is the fractional density change, and these quantities are the connected to by Euler factor, but these are the order parameters. So, in this example, phi naught phi g are the order parameters. Then in the gas liquid transition, it is the rho liquid minus rho gas, that is the order parameter. Magnetic and ferromagnetic transition, magnetization is the order parameter. Gas liquid is difference. Liquid solid, the phi naught phi g order parameter. Sol gel viscosity is the order parameter. So, it is a quantity which is 0 before the transition, becomes non-zero after the transition. This was Landau definition. Now, why did Landau define it? Why did Landau define it? Okay, Landau defined it because Landau had in mind to describe a phase transition. So, Landau was looking for a quantity. See, in physics, when you want to describe a change, we want to quantify the change. Why want to quantify change? Why? Because if I describe a free energy, then I want a smallest parameter. The smallest parameter is the one that I can expand free energy about, and that smallest parameter is the order parameter. It is something which is 0 and then become non-zero. So, I can do a Taylor expansion in the smallest parameter. So, order parameter becomes the smallest parameter in my Taylor expansion, and that was the idea of Landau, and that is a very beautiful idea. That now there was, when this was done, this another brilliant physicist name is Ehrenfest. Ehrenfest came up with it. He noticed something very interesting. He noticed that there are some phase transitions where entropy undergoes a jump, like melting, and then liquid solid transition away from the critical gas liquid transition away from the critical point. There is a jump, like in water, 40 kilocal per mole, kilocal per gram for gas liquid, 80 kilocal per gram for calorie gram or kilo, I don't forget those, but they are finite change. However, when you go to critical point, then specifically diverges, no change in latent heat, and then magnetic transition, paramagnetic ferromagnetic transition. If in the absence of a magnetic field, it is a transition which is again continuous, but has this divergence, peculiar behavior. Superfluidity has this peculiar transition. Then order disorder transition solids like brass shows these characteristics. This shows these characteristics where second order properties of free energy undergoes divergence. But in the melting, it is the first order property, is entropy, it is the first derivative of free energy. So, first order property means when I have an order parameter and a control parameter, I change that control parameter, first derivative of free energy becomes discontinuous. So, Ehrenfest said, let me now capture this universality across the phase transitions. That first order phase transition are those phase transitions where first derivative of the free energy is discontinuous, and second order was the second derivative of the free energy with respect to order parameter or control parameter become discontinuous. Suddenly everything kind of falls in place. Oh, now I say, when I say first order phase transition, I know the characteristics of first order phase transition. Whatever that the material is a gas liquid transition from the critical point, or melting, or magnetic transition in the presence of a magnetic field, all have the same characteristics. Similarly, in a second order phase transition, it is second derivative of free energy, but most of the second order phase transition actually continuous transition like the critical point and superfluid transition, except one. There is one truly second order phase transition in Ehrenfest sense. The second derivative shows it is continuity, and that is the most important transition, is the superconductivity. But however, there are all these little qualifications here and there, but Ehrenfest introduced a very powerful paradigm saying the order of a phase transition, following order definition of order. Now Landau theory comes in beautifully. Landau says, okay, I now know, I can describe the free energy, and I can describe the, so this is the hysteresis and metastability. Then what shows in the presence of a magnetic field. So, H is the magnetic field and is the magnetization M. I change that. However, behold that I am switching the size, but even after switching, it does not reverse immediately. It hang on and then go. While again switch the other way around, it is a long time. So, this hanging on the old phase is called metastability and hysteresis, and this is the trademark of first order phase transition. Second order phase transitions never show metastability or hysteresis. This is very, very important. and this is what led Landau to develop his beautiful theory. So, again come back, why does a system show such sharp change? What is the origin of discontinuity? Then how can we calculate? How can we calculate? How can we evaluate the transition parameters like latency? What are the order parameters? Then why liquid sodium goes to BCC and while argon goes to FCC? These are the questions one would like to answer. This is where Landau now came in. Landau, these are the things, stability analysis, that when does one system become stable, and one talks of convexity and concavity. Like for example, I draw the line between the two minima, then if the curved line above, then it is convex. However, if it lies below, then it is concave. So from stability to metastability, stable phase to metastable, you will have everywhere this convexity, but however the other early you will have the concavity. So these kind of things analysis done in terms of first and second derivatives as the energy is done here. But that is very interesting, but not the stability analysis, and it essentially goes back, the specific heat has to be, and I told you that specific heat nothing but delta E square 0 is the average of a fluctuation and square of a fluctuation. Fluctuation can be positive or negative, but square has to be positive always. So specific heat has to be always positive quantity, and that's a stability condition. So minus CBD must 0, that means CP must be positive. These are very, this concave function and concave function that I described here. You can read it, and this, and I have done it little bit before, but you can do it yourself. But now I go to Landau theory, and in 5 or 10 minutes that I have, I'll just describe Landau theory. Landau theory is a beautiful theory which is based on the order parameter. Landau theory is a free energy expansion in the order parameter. Landau theory is the basis of almost all theories. This is a phenomenological theory, but it's a beautiful theory. And so is a mean, it is sometimes called mean field theory because some kind of fluctuations are neglected, but it's so main merit of the Landau theory that it introduced, it taught us to think in terms of order parameter, talk of the minima in free energy and free energy landscape. So this is the Landau free energy expansion. So Landau said once he defined the order parameter, Landau said, okay, now I know I can expand free energy. So he went ahead and expand free energy in terms of this order parameter. Eta is the order parameter. He said, okay, I am just a Taylor expansion. I want to describe, this is the free energy of the new phase, this is the free energy of old phase, this is new, this is old. And he wrote down a Taylor expansion, that all of us know the Taylor expansion, right? Very simple Taylor expansion. Now we know Taylor expansion. We know now Taylor expansion, if I have to give alpha, I will take dfd eta at the old phase, and I get alpha, the way we do the extrapolation and interpolation of a function. But in my case, that first derivative of order parameter free energy, but free energy has to be minimum because it has to be stable. That's why we did all the stability analysis. Then what does it mean? That means this quantity cannot be there, alpha has to be 0, because the free energy of the old phase must be minimum. But how do I, but that does not apply to this. So I can now get the secondary AT. I can get AT by taking this second derivative of free energy and then evaluate it in the old phase. That's what we tell expansion. We take the derivative but evaluate it in the old phase. AT, B and all these quantities are temperature dependent, and they are obtained in terms of the old phase free energy. And now, so this is now Landau free energy by introducing this condition, and eta is my order parameter which is used as a smallness variable in expansion. This is just beautiful. Now, what did Landau do now? Okay, this again I am writing this thing. He then said, okay, let us think of metastability and let me think in terms of hysteresis. So, if there has to be hysteresis, then I must be that when I am hitting this, there should be a minimum. So, it is getting stuck in the minimum, and though I am this new phase is more stable, old phase still remain a minimum. So, that explains metastability. What does that mean? That means I have this kind of structure of free energy. That means I have one deeper minimum, one less deep minimum. How do I get such a minimum? I can get such minimum by keeping the odd terms here. However, in critical, so this is the first order phase transition where I need to have these odd terms. I will not talk of these things, I will just talk of this fourth up to fourth power. However, in a critical phenomena, there is no metastability, there is no such no hysteresis. So, two minimum odd net, then how does second order phase transition, the so important transitions in a critical phenomena, then magnetic transitions happens. That then he is argued very nicely. He said, okay, that happens in the following fashion. He said, in that case, the one minima that becomes flat and it becomes increasingly flat, and then it just becomes two phase the same. So, if I go to this critical phenomena point, temperature against density in gas, liquid or binary mixture, I am coming down like that, then the minima in the gas phase, there is a gas, minima in the gas phase is becoming flatter. Remember, second derivative of free energy is the compressibility, that diverges, it becomes infinitely compressible, and that then suddenly when you go below the critical point, two minima appear, that of the gas and the liquid. Look at the symmetry, this is called the symmetry breaking transition. So, how do I describe that now? Okay. In the second order phase transition, I go back to my Landau theory of this expansion, I will come back this little bit later, and then I say, okay, there is the new phase I am going to describe has the symmetry that at plus eta and minus eta free energy is the same, this is called parity. Then this is the condition. When I said that, odd terms disappear, it remain only the even terms. And in the even terms, there is a very important quantity now. This is the free energy old term. The A is the quantity that is the spring constant, because this is the harmonic. If I forget for a moment of this thing, this is the thing that gives rise to this two minima. But before two minima, this is becoming flatter, my getting flatter. Who describes that? This quantity describes the flat. That means this quantity, which is the spring constant, which holds the system together, which is second derivative of free energy, is becoming smaller and smaller. How do I describe that? And this is the brilliance of Landau. Landau said, okay, let us assume that happens linearly. It happens that this A temperature dependence goes to 0 at critical temperature is approached, and that goes, so he assumed T minus Tc, and this is given by the time derivative of the free energy, temperature derivative of the free energy. Okay, now it changes sign in this quantity now changes sign at Tc, this becomes this is the second derivative of the order parameter, but first derivative is temperature. Now, because this quantity is compressibility, so it has, that is why it is a second order phase transition we are talking. So, this quantity now is made to change sign. So, as soon as they are changed sign, this it become minus and become plus, that gives rise to these things. So, this is the Landau essential. Then one goes on and doing this, okay, then one solve for eta. We take the, if these are two minima, then that satisfies the minima condition, that means derivative of df d eta has to be 0, and then I do this this term, this quantity, and this a, I put a equal to t minus Tc, and I take the derivative, and I get this, and eta equal to 0 is the maximum, which is this solution, the trivial solution, but then I get two values, one is for this one and this one, equal plus and minus. However, the beauty is that this order parameter, this value, the value from here to here, where the minima scales in a funny way, Tc minus T to the power half. This is the critical exponent or exponent of the called critical exponent or Landau exponent or mean field exponent. That is something more needs to be done. So, this is Landau theory of critical phenomena. Then one can go on second order phase transition, one can many things are like that, magnetic transition, weakly first order phase transition, then superconductivity, isotopic nematics, MACTIC is weakly first order, almost second order phase transition. Order disorder is a second order phase transition. Gas liquid at critical point is a second order phase transition. There are huge number of things that happens in the second order phase transition. So sorry, I have to now go back and do a little bit. So this is the way second order phase. First order phase transition is done like van der Waals. Now we cannot ignore the cubic term. We cannot ignore this term, because that gives rise to metastability. And one can again go back and do one thing, van der Waals gas, we can do that. So this is the van der Waals equation, the free energy. Starting from this equation, I can integrate, because free energy is dVp, and put this, then I can get the free energy, and that is this quantity. Now I do what Landau told us to do. I do an expansion in density. Density is the order parameter. I told you gas liquid transition. Then I get this beautiful thing, which is nothing but the Fourier series, and that now describes this phase transition Landau and describes the free energy that one can show. That this is essentially very much, this is the ideal gas part, and this is the part that describes this free energy with one deeper than the other, the asymmetry in the first order phase transition. From learning from Landau how to do it, go back to van der Waals and we can describe that. Okay, so I think this is the, we'll stop here today. This beautiful area of phase transition. I have done it little bit before. I did more now. Many things I forgot to say in the first time to give you students more physical insight, but now I have done it here a little bit more. So from now we'll go on to doing few more things in phase transition in the next class. 1 or 2 more class will be on phase transition. Then we'll go back again to do statistical mechanics of what what we'll do in phase transition essentially will be simple, will be phenomenological Landau theory, because of the generality. It is so general, the things of phase transition, that it is better to have a very general description. That means we need not talk of intermolecular interactions like Mayer did. When we talk of intermolecular interactions, we are demanding much more. We are doing so much more work. We need to then get exactly the values of parameters like latent heat. What are the order parameters? Then it's okay, justified to do a very detailed calculation. But then each calculation has to be for each phase transition. I want to do a melting transition, I have to do theory for melting. Well, still Landau theory in the background, but I have to do freezing, that will be different from melting, because the phenomena, though they are thermodynamically or reverse of each other, StatMech, they are very different, because liquid going to crystal is different from crystal going to liquid. But if I want to do in terms of thermodynamics, the general parameter, then again Landau theory comes in. Then Mayer's theory as is such a detailed theory. So the goal is different and our work is different. These things are extremely connected to each other, and a scientist, a physical chemist or a physicist knows what is time and then develops the theory particular to the need of the time, the need of the moment. Okay, thank you. We'll see you in the next class.